Hi, my name is Adi, and I am a senior at NYU studying psychology and data science, and I'm the president of the Data Science Club at NYU. This is Data Science Club Deep Dive, which is a series of lectures that we're hosting about machine learning. Today, our lecture is.
Hi, I'm Kenny. I'm a current second year at NYU, and in this episode of DSC Deep Dive, I'll be teaching IE about neural networks, as convolutional neural networks.
Nice.
Yeah,
The convolutional kind of neural
convolutional.
networks.
Yeah, that's very important.
Very important. I guess that's the whole point, huh?
Yeah.
Okay,
All right,
cool.
sure.
Very exciting.
Okay, so let's start. In this part of the tutorial, I'll go over the intuitive reason behind why CNNs work. In the next part, I'll go over how they actually work. Image of a 5. How do we know that it's a 5 and not some other number? Well, you might answer, there's a flat part on the top, a slanted part on the left connected to the top line, and a rounded part on the bottom. Sounds like a bit of a silly, easy question you'd ask to a kindergartner, right? But this very simple question has very profound implications for how we can create and train AI to see in the same way that we do. Let's leave kindergarten and head to the machine learning lab. How would we design an AI which can see in the same way that we do, by breaking apart images into their individual features and recombining them? This is a much tougher question, and one that many AI scientists have attempted to answer. After much experimenting, AI scientists created the Convolutional Neural Network, or CNN. CNNs form the foundation for modern research into computer vision, an area of machine learning which deals with how AI processes visual data and images. Take the abstract problem of teaching AI to see like us into a specific problem. Given an image of a handwritten digit from 0 to 9, how would we train the AI so that it's able to recognize the image as a digit from 0 to 9? A traditional way to approach such a problem would be with the multi-layer perceptron, but this has three issues. The first is shift invariance. The multi-layer perceptron takes in as input the entire image at once, which may cause issues when an image is shifted in the frame. For example, a 6 shifted extremely to the right may cause the multi-layer perceptron to mess up, as would a 6 shifted extremely to the left. The second issue is the large number of weights, which makes training costly in terms of time. 3. Multi-layer perceptrons don't see in the same way that we do. CNNs were designed to get around all three of these issues. How exactly do they function, and how are they better than multi-layer perceptrons? Convolutional neural networks operate on the convolution operator, which happens between two different matrices. For a simple example, let's consider the following image I and a filter f. We will pass the filter f over our image I. Let's consider the four elements in the upper left-hand corner of our image and our filter f. Note, when we're convoluting, the subregions which we considered each convolution must be the same size as the filter. We will take the element-wise product between the elements in the upper left-hand corner of our image with the filter, and then we add them. For example, the 1 here in the image subregion corresponds with the 1 in the filter, so we multiply them together. Same for the 2 in the image, and for the 0 in the filter. They're corresponding, so we multiply them. Same for the 4 in the 0, and same for the 5 in the 1. So we take all these products, and then we add them, and we get a 6. And this will be the first output in our convolution, and it will go in the upper left-hand corner of the output matrix. We slide our filter over to the right 1 unit, and we consider the upper right-hand corner, and we sort of repeat the same thing. So here we have the upper right-hand corner, and here we have our filter. So this 2 in the upper right-hand corner of our image corresponds to the 1 in our filter, so we multiply them and add. The 3 and the 0 correspond, we multiply. The 5 and the 0 correspond, multiply. The 6 and the 1 correspond, multiply. And after we've multiplied them all, we're going to add them, and we get out an 8. And since we slid our filter to the right 1 unit, this 8 is also 1 unit to the right of our 6 in the output matrix. And after we've performed this element-wise product and added, we can't really move any further to the right, since we've reached the edge of our image. There aren't any more elements over here. And when this happens, we need to move our filter to the left-hand side again, except this time we're 1 unit lower. This corresponds with the 4 elements in the lower left-hand corner of our image. Similarly, in the output matrix, we start again on the left, but we're one row lower. When all is said and done, our output looks like this. And this is a very simple operation, but when we apply it beyond our simple example here to image data, it can be immensely powerful. let's take a look at how CNNs process images. Look at the following MNIST digit, which lives on a 20 by 20 grid. To us, each box in the 20 by 20 grid is grayscale from white to black, but to the computer, each box holds a number, and a darker color, like right here, means a larger number. This makes it a lot like the eye from the previous example. To get from our input to the first convolution layer, we'll pass k different filters over the image. To do so, the procedure is very similar to our example. We loop from 0 to k first. Then, after we've selected one of our k filters, we start from the upper left-hand corner of our image. We take the elements product of that corner with our filter, we add the products, and then we take that sum and put it in the upper left-hand corner in the corresponding output matrix. Then, sliding our filter over to the right 1 unit, we repeat the same procedure, inserting the sum into the element which is 1 unit to the right of our upper left-hand corner of our output matrix. We then move again to the right, etc. In the convolution process, when we reach the right edge of the image, we need to start on the left edge of the image again, except this time we're 1 unit downward. Now, one key thing to note here is that unlike our example above, each filter represents something. They represent a critical feature we're looking for in the image. For example, our filter F here could look like this when we zoom in on it. This looks like the right end of a line segment. Remember that each box in this image represents a number, not a color, to the computer. The fact that we're sliding the filter over the image is crucial. This is exactly how our eyes see. As part of our visual processing, we look an image over and we identify crucial features. As we slide this filter over our image, we don't really have high values until we reach the bottom right-hand corner, where it fits really well. Here's one other thing which is different from our example. If we have high values in a certain box in our output matrix, it means that the subregion in our image corresponding to that box matches the filter really well. For all k filters, and we get our k feature maps. At this point, we will feed each of our output matrices into a ReLu function, which we define in the following way below. ReLu x is equal to x if x is greater than 0, and it's equal to 0 if x is less than or equal to 0. When we plot this function, it will look something like this. Why do we do this? The point of this transformation is to ensure that only positive values remain in our k output matrices. If a value in our output matrix is negative, chances are it doesn't match up with our filter, so we get rid of it. To include our k output matrices, we also need to pool them. The way that the pooling layers work is like this. We split up our matrix into 2 by 2 boxes. Taking a look at the example below, we would have 4 such boxes, each one a different color. The pooling operation is simple. We simply return the largest element in each 2 by 2 box. For example, the 6 is the maximum from the upper left-hand corner, the 8 is the maximum from the upper right-hand corner, the 14 is the maximum from the lower left-hand corner, and the 16 is the maximum from the lower right-hand corner. Why do we do this to our k output matrices? We do it for a similar reason to the ReLu. We only want the elements in our output matrix which have the strongest relationship with the filters to pass through to the next layer. Note that the locations of the highest values in our output matrix represent the locations of the subregions which match the filters the most. Convolutional layer. Before we dive into it, there's one more critical thing about convolutional neural nets. Higher level convolutional layers learn to put together information from lower level convolutional layers. This key property is key to understanding how CNNs learn to see things in the same way that we do. Layer is now k different filters instead of a single image. We changed the way that we do our convolutions just a little bit. Instead of sliding a single filter over a single image, we slide k different filters simultaneously over our k images. To see how this works, let's do a simple example. Suppose that we have the following image here, P, where P is made up of 2 different sub-images. So since we now have 2 input images, our filter will really be made up of 2 different subfilters, as we can see here. So we're now going to pass over the upper left-hand corner across both images. For example, this right here is the upper left-hand corner of our first image, and this right here is the upper left-hand corner of our second image. So we're going to take the upper left-hand corner of our first image, and we take the elements product of that with the first subfilter, and we take the upper left-hand corner of our second image, and we take the elements product of that with our second filter, and we're going to add. So right here is the sum of the elements products of the first sub-image with the first subfilter, and this right here is the sum of the elements products of the second sub-image with the second subfilter. And when we add all of these up, we get 97. And this will go into the this will go into the first element of our output matrix. Previous example, sliding our filter over the image, doing LMI's multiplication with our filter, and adding until we get our output matrix, which is right here. So here's one critical thing to note. Even though our filter is made up of multiple subfilters, it's still only one filter, and that's why there's only one output matrix. Now let's apply it to our k output matrices from the first convolutional layer. Suppose that we have m filters for the second convolutional layer. Then, each of those n filters will have k subfilters. Furthermore, after the convolution, we're going to output m output matrices. Before we proceed further, let's see how exactly our second convolutional layer puts together data from the first convolutional layer. Let's consider 3 out of our k filters, and suppose that the 3 filters look something like this. For example, this looks like the left-hand side of an arch, this looks like the center of an arch, and this looks like the right-hand side of an arch. Now, imagine that we pass it over our image, and we get really high values near the top of the output matrices, which correspond to these filters. This means that our image has features really similar to these filters near the top. For example, after passing through the 3 filters, our 3 matrices on the output layer could look something like this. For example, this is the matrix which corresponds to the left-hand side of the arch on the previous slide. So basically, we can see that this 16 is the highest number in its local area, and essentially what that means is that the subregion of our image, which corresponds with this 16, it matches with the left-hand side of an arch the best relative to the other subregions which are near it, arch near the top. We'll pass through the filter corresponding to the arch through the output matrices from the first image. When we're near the top of the first layer output matrices, the values in the subfilters in the arch filter should closely line up with the values in the 3 output matrices from the first layer. For example, let's return to the previous slide. So this is the output matrix which corresponds to the left-hand side of an arch. So if we take a layer 2 subfilter and slide it over that region, and we get a high value, when we take the LMI's product and add, essentially what that means to a neural network is it means that, okay, we probably have the left-hand part of an arch in this portion of the image. And then we do the same thing down here. We slide another layer 2 subfilter over this output matrix, and if we get a high value when we take the product, essentially it means to the neural network that, okay, we probably have the center portion of an arch in this region of the image, and we do the same thing down here. We slide a subfilter over this output matrix, and if we get a high value when we take the LMI's product and add, essentially what that means to the neural network is, okay, we probably have the right-hand part of an arch over here. And remember that for ladder convolutional layers, when we do the convolution operation, we need to add, and that addition is what puts all of these features together. So when we add the LMI's products, essentially it says, okay, we probably have an arch, we probably have the left-hand part of an arch over here, we have the center part of an arch in the middle, and then we have the right-hand part of an arch on the right. So let's add all of these together and combine, and that essentially lets the neural network know whether we have an arch, an overall arch in the image. And essentially, this is the critical key behind how CNNs work. The first layer breaks apart images into their fundamental components, and subsequent layers put those components together and summarizes that combination, simplifying the image down. Afterwards, we can then ReLu, pool, etc. After this is done, we're ready to feed it into our multi-layer perceptron, and we get out 10 probabilities, one corresponding to each digit. If the digit with the highest probability matches the actual label of the digit, we're accurate. And that is part 1 of CNNs. In the next part, I will go into the technical details of how convolutional neural networks work.